Hey guys, it's EddieW, and today we are back and we are going to be talking about Turing machines and von Neumann machines. And these are really important things. And I've sort of been evading exactly talking about these for a while because I sort of wanted to let everything that has to do with these things avalanche down on you guys in sort of one video, so I've sort of been illusory, and I've sort of like not been telling you guys the full truth, but here you go, Turing machines and von Neumann machines. These things are super important, and without them, the world would be very different. So, first of all, let's talk about this guy, Alan Turing. You may have heard of him because he was the main character in The Imitation Game, which is a really good film. I suggest you watch it, but let's just say that it's not that historically accurate. Yeah. Anyways, the really important thing is that he created a concept for a machine that could solve any mathematical problem, including, as is shown in the movie, the Enigma machine that the Germans used in the Second World War. So yeah, that's basically what the point of Turing machine is. Anyways, so the machine is based off of a set of memory that you have a machine, and that machine basically just goes around and edits the memory according to a certain set of rules. Now, in order for something to truly be Turing complete, it doesn't just have to be something that edits this memory like that, it also has to meet a few qualifications. There's qualifications we're going to talk about now. So the first one is that it needs to have an infinite amount of memories, because if you're going to want to try to solve any problem, then you're going to need an infinite amount of possible amounts of data, because you could have like Googleplex squared or something digits, and you would still have to represent it. So yeah, you're going to need an infinite amount of memory. Anyways, so the next thing is that it has to be able to decide what to do next and create its own instructions depending on what happens. So for instance, if I'm solving something like, let me think of an example. Like, let's say that I'm trying to factor a polynomial, and one of the first things I might do is, if it's a binomial, then I might just try to do difference of two squares. And if I can do that, then I need to be able to write a program that's going to tell me how to solve the difference of two squares, or I might have to do something else. So yeah, and it's also useful for some other things in the terms of the actually writing the instructions part, but we're going to get to that much later on. Anyways, so the next thing is that the machine has to have a whole bunch of different states, and that's basically the thing other than the information that comes from memory that tells it what exactly it needs to do. So it might say, if it's in state 1 and you read a 1 out of the memory, then you might do such and such. But if it's in state 0, you might do something else. Or if there's a 0 on the tape, you might do something else. So yeah, that's basically the idea. So now here's to the big reveal. Turing machines are not the same thing as a computer, but they're very similar. A CPU is used to represent a Turing machine. Memory is just plain memory. We're going to talk about how it doesn't have to be infinite later. But states are basically your registers in your CPU. And it needs to create its own instructions, which we're going to talk about in a bit. But anyways, now let's talk about the memory for a second, shall we? Because with the devices that we have today, there is no way that we can actually make a Turing machine, and a lot of people forget this because we cannot have an infinite amount of memory. So, regardless of how powerful stuff is, modern computers still cannot solve any problems. However, the odds that we're going to need to solve a problem, like my example from earlier where you had like using numbers that are like Googleplex squared, the odds that you're going to need to use something like that are just so small that it's not even worth considering. So yeah, we just really don't need to have that much memory. I mean, it's sort of nice if we do, but whatever. Anyways, so now let's talk a bit more about the creating its own instructions, because the reasons why it's significant and why you need it in a Turing machine are a bit more complicated. If you really want to find a lot of this stuff out, I'm trying to sort of do a simple tutorial here. You should like actually read Alan Turing's paper where he actually wrote about this, but that's if you want to go like above and beyond. And also the language in that's pretty archaic, so yeah. Anyways, let's talk about this other guy, von Neumann. And so basically when computers first started to be made, there were basically two different kinds of memory that you would have. Instructions memory, which is basically like punched tape. If you've ever heard of old computers, then you'll know that they used this tape that you would put into the computer and you would have your program on that. And there was also some complicated stuff in that you might have more than one of these cards or tape or whatever you want to call it. And you would have like a stack of them, and then you would drop them accidentally, and then you had cool machines that could put them back together. But anyways, the other kind was just the normal memory that we think of today, just RAM, stuff that the computer can edit. And what von Neumann did is he reminded the world that in order to be Turing complete, you needed to have this distinction. So yeah, that's really important that you keep that in mind, and the reason that it's so important is that almost all Redstone computers, I've never seen a Redstone computer that is actually Turing complete. There have been specific Turing machines that I have actually seen in Minecraft, but I have never seen a Turing complete Redstone computer. And that's just because they're not von Neumann machines. So I'm sort of taking the role of von Neumann here and just trying to remind anyone who's watching this to make their computers von Neumann machines, because there's some programming advantages to having it, just a simple example for it would probably be like an operating system. If you want to be able to load in another program that you already have, then you're going to need something that's going to allow you to write that program without having to actually go into the computer and do stuff. So in operating systems or IDEs, that's where it's important to have stuff like this. But yeah, that is everything that we're going to be doing today, so I hope you guys have enjoyed, and I will see you guys next time.